Hello everyone, welcome to Pepcoding. So in this video, we are going to start another interesting question. The name of the question is pre-order merge traversal and a binary tree. So we have already discussed in-order merge traversal. So in this video, we are going to discuss pre-order merge traversal. Okay. And but before that, I want to tell you that if you have not watched the video of in-order merge traversal, then for that, kindly go and watch that video and then continue with this video, because with this way you will get a better insight of this question. Okay, because the main points will are already told in order video. Okay, so go and watch that and then continue with it. So let us discuss the question. So in this question we'll be given a binary tree. Okay, it is a binary tree and we have to traverse the pre-order of it. Okay, we have to print the pre-order of it, and for that we are not going to use recursion, we are going to use Morris traversal. Okay, we are going to use Morris traversal. So why Morris traversal? Because Morris traversal takes O1 of space, recursion takes O(n) of space. Okay, recursion takes O(n) of time, it also takes O(n) of time. So as the both time complexities are same, but the space complexity is different for both of them. So this is why we are looking into this Morris, because it has a better space complexity. Okay, so let us look into this Morris traversal, that how we are going to traverse into it. But before that, let us see how was our recursive solution. So in recursion, we used to do print a node, go to its left, go to its right. Okay, a call for left, a call for right, and in this way we used to print the pre-order. Right here we used to print the pre-order. So what happens, see, this is my Euler path. I start from 2. What I'll do, I'll print 2, I'll make its left call, go to its left, again I'll print 7, I'll again go to its left, so it will say go to 2 and print 2. Now 2 will say go to my left, so nothing will come from the left, nothing will come from the right. It will again reach to 7 and will reach to 6, so 6 will say print me and go to my left, so it will go to its left. So 5 will give nothing, but 5 will print itself, will make it both of its call, and then we'll go to 6. 6 will now execute its right call, so it will print 11 from that and it will go back to 2. Then from here it will come to 5 and will print 5. Okay, and then it will reach 9, will print 9 and go to the left of the 9, and 4 will print itself first, then make its left call, then right call. It will get nothing from it and it will go to 9, and in this way the whole stack will be empty. Okay, so this is my in order traversal: 2 7 2, and then 6 5 11, 6 5 11, and then 5 9 4, 5 9 4. So this is my pre-order traversal. So this is how we are going to traverse in recursion, but recursion was using stack space. Let me show you the stack frame that it was using. So it was like we know that, right, that print then left then right, we know that call and the printing statement, so not gonna write that again, but let me take the stack. So this will be my stack. Okay, this is my stack. I'm going to use this stack. So how I'll work in it is, see, first of all we'll go to 2. Okay, here I'll write my pre-order, so I'll print 2. Okay, 2 will be printed, 2 will say go to my left, so left of 2. So now 7 will print itself and will say go to my left, 7 left. Now we'll reach to 2, print 2, left of 2. Left of 2 will give nothing, it will say go to my right. Right will also give nothing, it will come back to 7, and this will go out of the stack. Okay, so when I'll reach 7, then 7 will say go to my right, 7 right. Okay, so 7 right. From here we'll reach 6, from here we'll reach 6, so 6 will print itself, it will say go to my left, so 6 will go to its left. Here we'll see 5 will print 5 and 5 will say go to my left, will give nothing from the left, go to my right, will give nothing from the right, take it out of the stack. So now it will again reach to 6 left, right? From 6 left, it will make the call of 6 right. So 6 right here. Now we'll reach 11. So 11 will print, and then 11 left will give nothing, then 11 right. 11 right will also give nothing. So it will come out of the stack. Okay, so it will now reach to 6. Now after reaching 6, it will see that both of the calls for 6 are done. So it will also come out of the stack. Then it will reach 7. So it will again see that both of the call for 7 are done. Now it will reach 2. So both the calls for 7 are done. Now this. Okay. Now 2 left is done. Now 2 right will take place. So here we'll do 2 right. So now we'll reach 5. So 5 will print itself, and 5 left will call itself. We will get nothing from the 5 left. We'll do 5 right. Okay. So now 5 right will reach to 9 left. But 9 will print itself, then it will go to 9 left. 9 left will reach to 4. And 4 will print itself, make its left call. We'll get nothing. We'll make right call. We'll get nothing from that. Then we'll reach to 9 left. So 9 will make its right call. We'll get nothing from that. So it will come out of the stack. 9 left was also done. Then it will reach to 5. 5 is done with both of its call. Then it will reach to 2 is also done with both of its call. So this is how the stack will be emptied. Okay. So as we have seen that in recursion we are using the stack space, right? And almost at least once we are filling an item, okay, and then after filling we'll printing it, okay, like it is processing, right? The same way that I have shown you here. So in this way, almost on of space we are using, okay, almost on of space we are using, but this space can be minimized using this Morris traversal, okay, because here we are not going to use recursion. We are not going to use recursion and any other extra space, okay, and not any other external stack or anything. We are going to traverse this binary tree, okay. So how? Let us see. So for this, as I have already told you in the video of in order traversal, we are going to use the concept of threaded binary tree. So in recursion we have seen that from here I can come to this node, right? I can come to this node because it erases itself from the stack when it will be done it with both of its calls, okay. So it will come here, and then from here I can also come here when it will be done. Then 5 will be done with both of its call, okay. And from 6 also I can go back to 7 because it will be done, 6 will be done with both of its call, and then it will come to 7, and then I can also come to 2, okay. So in this way I can traverse my tree in the pre-order as I have in any order with the help of recursion. But how I can do this without recursion? Because no stack will be allowed, okay, no pushing, no popping will be allowed. So how we can do this? See, for this, the threaded binary tree concept says you can go to this node to this, right? You can go from this to this. You can also go from this to this because you have link, right? But from here you cannot come back to this. Why you cannot come back to this? Because coming back to 7 you need a link. You need a link which a child cannot have. Child cannot have a link to its parent in a binary tree. In a binary tree, a child cannot access its parent, okay. So this is what we know. But what this Morris is saying that, okay, you cannot go back, but you can make a link. And let us call this link a thread, okay. Let us call a link a thread. So you want to go to 2 to 7, right? So for that I'll help you in making a thread. Somehow you will make a thread, and then you can go back, right? Yes, you can go back now. So this is thread concept, okay. Now from this I reach to this 7, right? Now what I want to go 6. I can easily go 6 because here is a link. I want to go 5. I can easily go to 5. I have a link. From here I need to go 6. So what I'll do, I'll make an this thread. This is also again a thread. Okay, so again I'll make a thread from this to this. Okay, from this to this I made a thread. From here I'll not make a thread because from here I don't need to go anywhere, but from here I need to go this end. So this is how my threads will be made in this binary tree. Okay, and with the help of these threads I'm going to traverse the whole tree. Okay, so let us see how we can achieve it. I hope that it is clear. This threaded binary tree is clear. I already have told this in previous video also, but still we are discussing it here. Okay, now, so what happens in my Morris traversal? We'll discuss that again. So I keep a pointer here, current pointer here, and a left node here, right? So we'll write this mark to discuss our time complexity again. Okay, that how many times a node is visited. So first node is here. Okay, and then I put a left node to the left of it. Okay, so let us see the conditions. Let us see the conditions of traversing. So from the starting, I'll start from the root node, right? And I'll go to left. I'll go to my left. So every time I'll go to my left. But when I will go to my right, someday I'll go to my right, right? But when will I go to my right? So the conditions for going right traversal, that means when I will go to right side, or we can say right side traversal. So when left tree is completed or no left calls remaining. What I mean is, see, if you are at this point, then you want to go to this, right? If you are at this point, then you want to go to this. So what this means is, this means that when this left side is ended, you have to go to right. That's right. Yeah, it is saying the same thing that we used to do in recursion. When the left side is completed, you have to go right. Okay, we got the point. And when left side is fully processed, see, from here also you go to right? So when you go to the here, we have not seen that my left tree is being empty. I mean, there is no left side. The here is left side is remaining, right? But from here I have to go here. How I can go? I will see that my left tree, this subtree, my left subtree is processed. If left subtree is processed, then again I'll go to my right. Okay, so these are some conditions in which I'll go to my right, and otherwise I'll keep on moving to my left side. Okay. So I hope that these points are clear. Okay, and we will see the conditions for printing also, that when we are going to print. So here is my C, here is my left node. So what I used to do, I used to find the rightmost node of this left node. So here is the rightmost node, and I used to check if the right of rightmost means right of rightmost this time is null. So I'll check if it is null or not. So if it is null, then it means if rightmost is null, right of rightmost is null, then that means need to create thread. That means here I need to make thread, so I'll create a thread. Okay, right is null, so it means that I'll create a thread here. Okay, so after creating thread, I'll print this too. Okay, I'll print this too. One more thing that you need to observe, that for every node that is having a left node, okay, this node have a left node, this node have a left node, this node does not have a left node, this node have a left node, this node does not have a left node. So every node that has a left node will be connected. Okay, have a connection. So all the connections, see, this has a connection, this has a connection, so this will come in my pre-order, this will come in my pre-order, This will also come in my pre-order, but this will also come in my pre-order, but it does not have my left node. See, you have to observe, it does not have my left node, but it should come in my pre-order. It does not have a left node, but it should come in my pre-order. It does not have a left node, it should come in my pre-order. It will not come in my pre-order. It will go like this. In this way, it will come to my pre-order. It will already come to my pre-order because I know that the one which has connection, it has connection, it will come. It has connection, it will come. It does not have connection, but it does not have a left node, so it will also come. It has a connection, it will come. And then it does not have a connection, or also it does not have a left node. So this is how I'll take it into my order, pre-order. Okay, so see, what I have written here is, when my rightmost right of rightmost is null, then I need to create a link. Okay, I will create a link. And the second thing is, I'll shift it to my right, I mean to my left. Okay, so here one time it is visited, second time it is visited. Okay, so I have I've sent it to my left. Now same thing, left node put here, make a connection. Okay, rightmost, find the rightmost is this only, 2 only. So check if the right of rightmost is null. Right of rightmost was null here, right? So make a connection. So we will make a connection. We made a connection. Now shift it to the left. Now this is an interesting case. This is an interesting case here. It is visited 2 times. Okay, one for the left node and one for this current node. So current node will come here now. So what will happen is, now when I create my left node, then it will be null. Left node will be null. So when left node will be null, at this point I am creating a connection. I'll print it. At this point I am creating a connection. I need to print it. I will print it. At this point I am not creating any connections, but here I can see that this person does not have any left node. So if my left node is null, then also I need to add it. So what I will do, I added 2, I added 7, I'll also add 2 again. Okay, I'll add this 2 and then we'll go back. Now as the left side is ended, right, here it is showing that the left side has been ended. It does not have anything in the left, so shift it to the right. When it will be shifted to its right, then it will be like this. Okay, so when it will come here, what it will do is, it will again make a left node here, but this time it will find its, when it will find its right of rightmost, then the right of rightmost from here is not null, it is equals to current. So that means it is the point. We know that this is a mark. I already told you in the video of in order that it is the mark. When we get the right of rightmost is equals to what? Is equals to current. Then that means at this point I have already processed this side. So when I have already processed this side, then that time I need to go to my right. Also I need to end this connection, because if I'll not end this, my tree will make some cycle, which I don't want. Okay, so as I'll keep this left node here, so it will be visited once again now, and now it will come to my right. Okay, so C will come here. Now C is here, put a left node here, make a connection. Okay, made a connection. Now what will happen is, from this, what will happen, it will go to the left. So from here C will come to this, so it will see. Okay, adding again. So it made a connection, add 6. Now C will come here. It has seen that it does not have any left node. So when it does not have any left node, add 5 and simply shift it to the right. The right of the 5 is 6, so it will be shifted here. Now my ln will come here. Okay, my left node will come here, and it will check if the rightmost of right is current now. So when it is equals to current, then what we used to do is, we used to go to right by ending this connection. go to its right by ending this connection. Okay, so now what I have seen is I'll put a left node here, right? I'll put a left node here, and after putting a left node, what I will do, I'll see that my left node is null. So when left node is null, add 11. Added 11. Okay, I added 11, and then what I will do, I will go to my right. So its right is here. So C will come here, and it will be like this. Okay, now again create a left node here, find the rightmost. Now the right of rightmost is not null, it is equals to some current. It is equals to current. So when right of rightmost is equals to current, then at that point what you need to do is, see, right of rightmost is equals to current. So what we used to do, we used to shift it to right side by ending this connection, as this connection is made by me. So end this connection, shift it to the right. Okay, and see, it will be visited once again to find ln. Okay, it will be visited once again to find ln, and will reach here. So when it will reach here, what it will do is, see, it will make its find its left node is null, so again it will add itself and go to its right. So when it will go to its right, what it will do, it will come here, so when it will come here, it will place a left node here and then will make a connection. So after making a connection, what it will do, it will shift it to the left. So current is here now. So when current is here, it will see the left node is equals to null. So when left node is null, okay, here we made a connection, and so we need to add it. And again, here at this point when left node is null, I need to add it. So I will add it, and then I'll go to my right. Okay, because left node is null means left side is empty, there is nothing in the left side, go to right. So when I'll go to right, I'll reach here. So after reaching here, what I'll do, I'll put a left node here. Okay, I'll put a left node here, and then we'll see what is the right of rightmost. Right of rightmost is equals to current. So when right of rightmost is equals to current, then at that point, what you used to do, destroy the connection. So destroy the connection and shift it to the right. So when it will be shifted to the right, then it will go to null. At this point, you need to stop. And this is the pre-order that you want. So where we have printed it, let us see where we have printed it. At the point, see, at the point when left node is null, at that point print, right? At that point, here when left nodes were null, we were printing at that. And other thing is, when my right of rightmost, see, when my right of right, I'm creating a link. When I was creating a link, that means right of rightmost is not equals to, is equals to null. I was creating the links when it is null, right? So when it is equals to null, then print. In these two conditions, I need to print this and this. Okay, so we will remember it. We have seen the dry run. Just write it into the code. So let us try to write the code for the same thing. Okay, again, one more thing. See the number of time it is visited. Number of time it has been visited is at least 3. Okay, might be some marks are missing, like some marks maybe are missing. Okay, because sometimes it happens that when we are dry running it, we don't remember exactly how many times we need to write this cross. Okay, so it happens sometimes, so maybe the number of crosses are come, but we have seen mostly we have 3 or 4 crosses, right? This is 1, so at least 1 will be visited everyone. This is visited 3rd time, 3 times, this is 3 times, this is 4 times, this is 3 times. So almost all are visiting 2 to 4 times, we can say. Okay, so average we can say 3 times. So if I'll talk precisely, the time complexity will be not in terms of O. The time complexity precisely will be O of 3n. Again, in the On terms will be big O of n. Okay, in On, if I talk in big O, then it will be On. But in precise, it can, we can say it is 3n. Okay, sometimes it goes to 2.7 or 2.8, but to be precise, or if in the whole number term, then we can say 3n will be the right digit. Okay, 3 1 will be the right term. So this is the time complexity. Okay, you can do it by your own, this dry run, you can do this dry run by your own, and I want you to put these crosses so that you can get to know that how many times a node is visited. Okay, so you will get an idea from there. So let us go to the board and try to write the code. Okay, so let us look into the code now. So we are going to code it in C++. So here we need to complete this function. Okay, input is already been handled. You just have to write this function and return a vector which will contain the pre-order elements. Okay, so let us write the code. So what I was doing is, first of all, I was making a current, right? So this will be like tree node current, and that will point to root first of all. Okay, it is root, so it will point to root, and then what it will do, it will run till while current is not equals to null, till then it will run. And as we need to return a array list, so what we'll do, we will vector append answer. Okay, we'll write it, and what we will do, we are doing, let us see. So suppose it is our tree, my current is here, my left node is here. So what I used to do, I was finding my rightmost, rightmost, and then making the connection. And when I'm making the connection, then at that point I'm printing it, right? We already have discussed that when I'm making my connection, then at that point I'll print it. And second thing, then it will shift it to this, then the same thing, it will make the connection, will print this, it will shift to this. Then at this point it cannot make a connection, but it should be printed. This node should also be printed. So when my, okay, so first of all, left node will also be printed, right? So let us write here a left node. So tree node left node is equals to tree node left node is equals to, it should be equals to current dot left, current. Okay, so here we have a left node, so we will check if my left node is null or not. Okay, we will check if my left node is equals to null, or if it is not null, then we will do something, and if it is null, then we will do something. If it is null, means that, see, my current is here, my left node will be at null right now. So right now it is at null, so this is the condition. So at this condition, what I used to do, let's see this from the beginning. So this is my tree, this was my tree. So when my current is here, my left node is here. Okay, I have made a current in my root. Okay, placing the current at my root, and then I made a left node. So my left node is current dot left, so it is here, my left node is here. I'll find when it is not equals to, when I will be at this block, when it is not equals to what, when it is not equals to null. At this point it is not equals to null, right? So when it is not equals to null, what I'll do, I'll find the rightmost, make a connection and print the C. Okay, and then shift it to the right, I mean to the left. So C will come here. Okay, then C will come one day C will come here, I mean at a point C will come here. So when C will come here, it will see that it cannot make any connection, but it should print itself. So when it will print itself, how it will print itself? So when my this point, okay, when my this point will come, that means when my node dot left is null, left node is null, then at this point add it to pre-order and shift to right. Why shift to right? Why shift to right? Because here at this point we already have discussed that my left tree is ended. It is not completely processed, but I know that it left, the left calls are being ended. I cannot go to more left. Okay, so go to the right now. So what I'll do, I will answer dot pushback. Answer dot pushback. I'll push back my current data. Current dot where, and then current is will be shifted to its right. Right. Current will be shifted to its right. So current will go to, see, from here to here, a link, when I will reach here, a link will already be created. So current will move again to this, okay, from to its right, and it means current will go to this. So it should be like this only, right? From here in recursion we used to go here and then here. So we are doing same in the model traversal also. Okay, so I hope this point is clear. So let us go to this point. So at this point, what we used to do, we used to make a rightmost node. So pre-node rightmost node is equals to, I'll make a function get rightmost node. Okay, get rightmost node, and I'll trust that it will give me the rightmost node. Get rightmost node, and we will give it a left node because I need the rightmost of this left node, and we'll give it current because we already have discussed this in our in order video that my left node will be same if it is pointing to current or not. Okay, my tree left node or the rightmost node will be the same. So at this point I have my rightmost node, so I'll check if the right of rightmost, if it is connected or not. Okay, if it has some connection or not. So rightmost node, right of rightmost is equals to null. If it is null, that means it does not have any connection right now. So when it does not have any connection, then at that point you should make the connections. So then at that point, make connection or thread. Also add that to your pre-order. Okay, this is what you have to do. So add it to the pre-order and shift it to the right, and here add it to the pre-order, make connection and shift it to the left. So what I will do, answer dot pushback current val. Okay, this will be done, and then current will go to its, okay, need to make connection also. So that means rightmost node dot right was null before this, but now rightmost dot right will point to current. Okay, and then current will go to its left. Now connection is also already been made. Okay, thread is already been made, and current is also shifted to its left. Okay, so this is done here, and here at this point it does not have any connection. That means if we came here, then it means that we need to destroy connection as it already have a connection. Okay, destroy connections, yeah, because we need to preserve our original tree. Okay, if we will not destroy the connection, then the tree will be completely changed. Okay, so what to do for reversing these connections? So the rightmost node, simply rightmost node dot right, not dot, rightmost node dot arrow right is equals to null, right? Simply, if we will do this, then this is how you will remove the connection, and after removing you also go to the right side because my left side is already been processed. My left subtree is processed. If I'm finding a node is already been attached, a connection is already been made, then it means that I have did the work for this subtree. I made this connection, I did this work, so I should go to my right. So That means current is equals to current dot right now. Okay, current should go to its right, and rightmost not dot right will be equals to null pointer, and at this point pushback. Okay, yeah, everything is almost done, just remaining this tree node star get right RIGHT, right, right most node, tree node, left node, comma, tree node current. So these two will be passed, and what it will do, it will give me the rightmost of this left node. So while left node dot right is not equals to null PTR, and rightmost and then left node dot right is not equals to current. Okay, in these two cases it means it is traversing in the right path, and if it is, then shift it to the right. Left node is equals to left node dot right. Any condition will hit, this loop will stop, and at that point that will be shifted to the rightmost place. So return my left node from there, because the left node will be at the rightmost point, right? The leftmost node is at the rightmost right now. So here I'll get the rightmost node. So it is done. And yeah, from here I need to return. What I need to return? I need to return answer. So let us give it a run. Let us try to give it a run. And I hope that it will run in the first run only. Some compilation error are there. 20. It is saying in line 20. So in 20. So here it is. Left node dot right is not equal to null pointer RIGHT. Okay, is not equal to current. Some compilation. Okay, 31. I have written null somewhere. Okay, yeah, 31. It is not equal to null. It is null pointer. Okay, yeah, it is accepted. So let us give it a final submit for all the test cases. Code is completely accepted. So I hope that you got this question. And if I'll talk about the time complexity, then we already know that the space complexity, the time complexity is precisely 3n. Okay, precisely 3n, because every node is visiting almost 3 times. Okay, some are visiting 1, some are visiting 2, but most of the nodes are visiting 3 times. So we'll say 3n is the average time complexity. Okay, precisely. And if I talk in big O, then it is big O of n, the space complexity of O1. That is why we are using this Morris traversal. It is better than recursion approach. Okay, so I hope that you got this question completely, and after this we'll meet in the next video with the next question. Okay, so till then, goodbye, take care, and don't forget to like the video and subscribe the channel. Goodbye.